So when we are working with our tests, our hypothesis testing, we need to decide from the setting of the problem what kind of a test we want to do. A left, a right, or a two-tail. But that's going to depend on what our hypothesis is, our null hypothesis. And that's, again, we have to take that from the context of the problem. Here are a couple of examples. Page 326, problem 7. A manufacturer claims that its compact fluorescent bulbs contain an average of 2.5 milligrams of mercury. They contain an average of 2.5. My null hypothesis is everything's okay, we're correct. How would I write that? Left, two, or right? I claim these bulbs contain 2.5 milligrams of mercury. Of those three null hypotheses, which one does that sentence sound like? Aha. So if that's a two-tail, then my assumption would be that my null hypothesis is that the mean is 2.5 milligrams. And its alternate hypothesis would be it's anything else. Same page, problem 9. The Scottsdale Fire Department responds to fire calls in 4 minutes or less on average. 4 minutes or less on average. Left, two, or right? Want to know whether or not the Scottsdale Fire Department is responding to calls the way they say they are. My null hypothesis should be they're correct. Scottsdale Fire Department responds to calls in 4 minutes or less. Right tail. The average time is less than or equal to the number I've claimed. So my null hypothesis, the average time is less than or equal to 4 minutes. And the alternate hypothesis is that it's bigger than 4 minutes. So that's how I decide what the hypothesis setup is. I make the assumption that the null hypothesis is they do what they claim, or this is a correct statement. I'm looking for something unusual to tell me, no, this might be wrong. And that's our alternate hypothesis. So now I have to make a decision. Should I keep the null hypothesis or reject it? So I go out and I take my sample. In this case, since I'm looking for information about an average, my test statistic should be based on my sample average. And then I look at the sample distribution. And we know that the sample distribution for an average is a normal distribution. And somewhere I'm going to be able to figure out a critical value. And I'm going to decide, am I too far away? Now, for the right tail test that we were just talking about, I take my discussion, I look at my average response time for the Scottsdale Fire Department, and I say, oh, is it too much bigger than 4? A right tail test means I'll be way out here to the right. Something's wrong. The two tail test, I take my sample of light bulbs, I measure the mercury in each of those compact fluorescent light bulbs, and I say, is it too far away from 2.5? If I were doing a left tail test, I'd ask, is it too low? But if I'm talking about mercury and other pollutants, I'm pretty sure you can never be too low. You can only be too high or different from. So if my test statistic is in the rejection zone, then I'm in trouble. The cutoff is based on my alpha. Alpha was our confidence level. So the rejection zone has a total area of alpha. So I wanted to be 95% certain, and the 95% is the unshaded part, and the 5% is the shaded part. In a right tail test, that means I need to know the value where I cut off 5%. The critical value is determined by our choice of alpha. The smaller I make alpha, I get fewer type 1 errors, but this makes it harder to reject my null hypothesis. How am I going to decide on that value? Well, that's going to depend on what we know about our population. The critical value is either a z value or a t value. And I'm going to make the same choices that I made about confidence intervals here. So I'm going to decide to use a z for a mean, depending on whether or not I know what. How do I decide whether I should be using a z or a t? I need to know what I know about the standard deviation or the variance in either case, right? But I need to know the population standard deviation or variance. Huh. If I know, then I can use Z. And that's what my test statistic is. If I either know the standard deviation or the variance, then the distribution for X bar is normal. And if I know it's a normal distribution, like I have a normal population or I have a large enough sample that I use the central limit theorem, then I can compute a test statistic based on the average. The Z value, which I am going to call my calculated Z value, Z sub calc, for exactly that, is the average minus my benchmark divided by the standard error. Notice that's not the same sigma that I said we knew up there. This sigma is the population. This is the standard error. How do I get one from the other? You have a formula for that. It's the same one we used in confidence intervals. There's something else that goes down here. Another way to compute this. Standard error depends on my sample size. What this is telling me how far away from the benchmark I can be in the normal distribution just based on random chance, as opposed to something is different about my sample. For example, let's go to the light bulb setup. I gather all my light bulbs and I take a sample of 10 light bulbs and I go compute the amount of mercury in each of those light bulbs. And then I say, oh, the Z I've calculated is 1.9. Maybe I'm just pulling a number out of thin air. Or maybe it's 2.7. Or maybe it's -1, right? I got a sample and all the mercury levels were low, lower than the 2.5 I was looking for. But I have a number. That's my test statistic. I need to compare it to a critical value. That critical value depends on alpha. But here's the absolute best part about this critical value setup. It is the exact same setup I used for confidence intervals. The homework you just gave me had you look up and use these exact same z-values. So now we're going to decide, am I doing a left, a 2, or a right? And that's going to tell me what my z-values are, my critical values. What I'm really saying is, if this difference is close to 0, then we're good. And if this distance is really big compared to the spread, we're not so good. So, based on alpha, 0.1, 0.05, 0.01. These are the most common choices of alpha. And then our critical value depends on whether we're doing a left tail, a two tail, or a right tail. So grab your tables, C table, or grab your calculator, because we can do this from there too. We're going to use the normal distribution. We can use table C2 or table C1. It's your choice. In a left tail test, remember the picture for my left tail test looks like this, where all the shading is on the left. If I'm doing a left tail test, I want this area to be alpha. I want that area to be 0.1. What is the appropriate z-value that goes with an area of 0.1? Well, based on that picture, that's exactly the same picture I see here in the table C2 picture. So I need to find the area to be 0.10. 0.10, there's my closest number right there. 0.1003, negative 1.28. Now, if you were to use your calculator to find that inverse normal, you'd get another decimal place, because that number was a little bit bigger than 0.10, it's 0.1003. Distributions, inverse normal. Area, 0.1. I can get more decimal places, right? As a matter of fact, I think the textbook actually writes out 3 decimal places, so it would write 1282. But if we just use 128, I'll be fine. Silly question. Right tail test. Switch from this picture to this picture. I just turn it to positive. I just take the picture and flip it over. Everything on the left goes on to the right. The negative numbers become positive. Okay, two-tail. Two-tail is now different, because when I do a two-tail, I need the area to be split between both sides. And that means it's cut in half. So instead of using 0.1, what do I use? 0.05. So I can go back through my table and I can look up 0.05. But again, that's a familiar sounding number. I did 95% confidence intervals. That would have been 5% on the outside, right? Same exact setup. 90% confidence interval, 5% on each side. That's the same number. And that means I'm going to get 2 z-values, right? A low z-value and a high z-value. Right here, one on each side. but they should be the same number, one negative, one positive. And it's a really familiar looking number. 1.645. Hot damn. By the way, if that's the number for half of 0.1, half of 0.1 is 0.05, right? That means that's this number right here. And this number right here. So what number goes in the middle in this line? A two-tailed test with a 5% confidence interval. Sorry, 5% confidence level. What's half of 0.05? Careful. It's not 0.025. It's just 0.25 or 0. What's half of 0.05? Is 0.025 or 0.025. To me, it sounded like you said two zeros after the decimal place. Because that's the one in the box. 0.025. 1.96. There we go. And there's a negative one and a positive one because we got one on each side. Unfortunately, that does not then translate down here because half of 5 is 2.5, not 1. So to do 0.01, I need either, for a left, I need the area to be 0.01. For the right, I need the area to be 0.99. We did these numbers. Point 0.01. 0.01. That's 0.01. There we go. Between these two, right? Oh, no, that's 0.001. I need 0.1. 0.1, here we are. 0.1. 2.3, closer to 3 than 2. We'll go with 3.6. 2.326. Oh, if that's the negative one, then the positive one over here, 326. And if I split it, I need to go to 0.005, and that's 2.576. All of these, all 9 of these numbers are here on page 328 with a lovely little picture to go with them to show you where I made these up from. I didn't pull these out of thin air. Now, this is a test. I made a test statistic. I need to know, how do I decide? I calculated some number. I have a value to compare it to. When do I reject the null hypothesis? Let's use 2.5 as our benchmark value. So that was my average claim, my benchmark for the mercury and the light bulbs. I gather up my light bulbs, I compute the average, I know the standard deviation, I work out the number, I get 1.7. I want to be 90% certain. My number is 1.7. Should I keep it, my null hypothesis, or should I reject it? What kind of a test were we doing for that light bulb setup? Left, right, or two? I was doing a two-tail. I came up with the number 1.7. My critical value is 1.645. Am I in the good region or the reject region? I'm in the reject region. I'm too big. I'm bigger than the right number on the critical line. I'm out here. I gather my collection of light bulbs. I do a test. The number I get is negative 1.3. Do I reject my null hypothesis? Because negative 1.3 is not bigger. It's not farther out, more negative than. If I switch my number from negative 1.3 to positive 1.3, I can think of it as not being bigger than, right? Let's take absolute values. I think that actually helps. We reject if the calculated value is bigger than my critical value. In absolute value, I reject if I'm in the shaded region in the rejection zone. But I have to know how confident do you want to be that this is right or wrong, and have to calculate my test statistics, which means in this case, I need to know the standard deviation. Page 332, problem number 17. Green Beam Limited claims that its compact fluorescent light bulbs average no more than 3.5 milligrams of mercury per bulb. Right there. That's enough to tell me what kind of test I should be doing and what my benchmark is. Compact fluorescent bulbs average no more than 3.5 milligrams of mercury. Left, two, or right tail? What is my claim for the null hypothesis? They are correct. The rejection is going to be if it's too big, right? So less than or equal to is the null. And the alternate hypothesis will be that the mean is too big. That's a right tail. The rejection zone is off to the right. And my benchmark is 3.5. A sample of 25 bulbs shows a mean of 3.59 milligrams. And this particular bulb manufacturer has a known standard deviation of 0.18 milligrams. I would like a test statistic. What Z calculated value do I get using this information? Remember my formula for calculating this Z calculated value, mean minus benchmark over the standard error. Very much in the same way we did Z's back in the first exam, second exam. Data minus mean over standard deviation. Well, I'm using the standard error instead of the standard deviation. For our problem, 3.59 minus 3.50 over 0.18 over the square root of 25. So sample of 25 bulbs, right? What is this number? Now, this is about light bulbs. This is about the environment because mercury is poisonous. If you break a fluorescent light bulb, technically, you are supposed to, if it lands on the carpet, supposed to cut out the square of carpet and throw out the carpet, the padding, and the underlayment in a secure environmental disposal system. Mercury is a very hazardous product. Not a good idea to play with it. So the EPA says, I want to be really sure that you are obeying your claims. If I want a confidence level, said confidence, I said that's the wrong word. Alpha. Alpha was we gave it a name. Alpha was our significance level. At a 1% significance level. Is the company lying to me? Or are they telling the truth? I need a critical value for a right tail test at 1%. We have that number. Or you can use your table to look it up. What is our critical value for this particular test? Crap, I made a copy error, didn't I? Yep. I made a copy error in my notes. 2.326. Do I reject or keep my null hypothesis? Because this number in absolute value is bigger than this one. What does that mean for this light bulb company? This group of 25 light bulbs had a higher average mercury content than you claimed. You claimed it would never be bigger than 3.50, and it is statistically improbable that I got an average of 3.59 randomly. There's more here than just blind luck. I happen to pick all the mercury heavy bulbs. Something's not right. It is possible that I could just get unlucky, right? I could have picked the worst bulbs in the whole factory today. How likely is it that I'm that unlucky? Another thing we can calculate based on our Z calculation is the chance of getting a number that far away from our average. We can think of the area in our normal distribution. What I could ask is, what is the chance that I got a Z value bigger than or equal to 2.5? Hey, wait a minute. I've seen that calculation before. That was the second to the last question on the exam, right? What's the chance it's that far out? You have a normal distribution. You have a table. What's the chance Z is this big? Aha. That number that you just gave me, how'd you get it? 0.9938. But table C2 measures from my Z value which way? From the left. I'm looking for area to the right. So what you gave me is the number Z less than, not Z bigger than. So what I really need to say is, oh, you gave me the right number. I just have to remember to do that and use my complements idea. And then that is 1 minus 0.9938, which is 0.0062. Really, really small. But here's another way I can say I should reject the null hypothesis. What was my sensitivity level? Alpha. Let me go back and pull up my numbers. Yeah, ta-da-ta-da. Oh, you're right, significance. I said the wrong thing. I wrote it down there, significance. Our significance level. You're right, beta is sensitivity. What's our significance level? It's 0.01. This is smaller than that. I'm going to call this a p-value. It's the chance of the thing I actually got as my result happening randomly. And if my p-value is smaller than my significance, I reject. That's a one tail. If I'm doing a two tail, I need to take the number I get out for p-value, multiply by 2. Because the chance of it being high or low, I've got two directions in the two-tail test. Again, there's a 1% significance level. I will only accept my null hypothesis if there is a greater than 1% chance that this happened randomly. This was really unlikely to have happened randomly. There's only a 0.6% chance it happened randomly. Reject.
Then you're talking about the detailed test.
Yes.
Did that, would you accept something, you multiply them together, 1, 0, 1, 4?
Yeah, and that would be bigger, right? So you see how my choice of test matters. If the light bulb company had said, we produce exactly 3.5. Oh, wait a minute. I would have gotten a different z-value, wouldn't I? What's my z-value then? Oh, but we're doing the p-test. No, you're right. I would have gotten a different z-value, but I'm using this and double that. That's too big. Yes, I would accept it. That's okay. Now you're saying the variation is acceptable. Two-tail tests have smaller areas, makes it harder to reject my null hypothesis. It's less likely I'm going to reject because I take that 1% and I split it into 2 0.5%. Problem 23. Here we go. An airline serves bottles of Galena spring water that are supposed to contain an average of 10 ounces. Filling process follows a normal distribution, standard deviation of 0.07 ounces. 12 randomly chosen bottles have the weight shown below. Let's see if the Galena spring water is filling at 10 ounces. All right, wait a second. At 10 ounces. What kind of a test am I going to run? Because you said at. If you said at least, you'd be a one-sided, or at most, you'd be a one-sided. Now, as a business person, I would like to know, am I producing 10-ounce bottles? And if I'm underfilling them, my customers are going to get mad. If I'm overfilling them, I'm going to get mad because I'm losing money, right? I'm giving them too much product each time. It's only water. I might not be all that pissed. But you never know. I was listening to the radio on my way home last night. I kid you not. Marketplace Reports did a report on haute cuisine water menus. People are drinking less alcohol. They go to the bar to find a particular bottled water that will accompany their meal properly. You've got to be kidding me. NPR, go look it up. It's the most amusing frou-frou article I've ever heard about. Okay, we were told the standard deviation for this process is 0.07 ounces. They actually gave me the 12 bottles and they gave me the numbers. There's a little data file name there that I can go get this off of our Canvas page and download the actual data, and I can run the calculation to give me the average. I already did that. The average I get is 10.015833. So here's my question. Is the claim from the Galena Water Company correct? Does my collection of data support their claim? I need two different numbers. I either need a calculated z-value and a critical z-value, or I need a calculated z-value and a p-value. But in both cases, I need a calculated z-value. Let's start there. Calculated number gets worked the same way. My average minus the benchmark over the standard deviation divided by the square root of the number of samples. What is that number? Oh, damn, I forgot to write that down. Hang on a second. In order for me to know a critical value or a p-value, which we hadn't gotten to yet, I need my level of significance, don't I? I haven't written that down. I don't have an alpha up there. I need to have that at some point. But that can come after this. What is my calculated z-value? Gotta get that buzz in there. Yes, same number I got. Great. The textbook says at a 5% level of significance. Does this data support their claim or not? I need to know, do you want to do the critical value or do you want to do the p-value? Okay, so I go back to my list and I say, what is the critical number for a two-tail test at 5%? The crit two tails Is the absolute value of my number bigger than the absolute value of that number? No. So I do not reject. If I were to calculate the chance that Z is bigger than 0.7, bigger than or equal to 7835, I would get 0.2167. This is a two-tail test. I have to multiply that by 2. 2 times 0.2167 is 0.4334. Is that bigger than our significance? A lot, right? This is our p-value. And p is much bigger than alpha, not smaller than. Again, that means we don't reject. P is not smaller than alpha. Do not reject. That's the actual calculation of a test. I think this water filling station is going fine. In spite of the fact that those bottles were a little more than the 10 ounces, good enough. Could have just gotten a dozen randomly slightly topped off bottles. More to come on Monday. I will see you all then. Have a wonderful weekend. Happy Halloween.